Hello, I am going to look at some design ideas and concepts for the National Semiconductor, now Texas Instruments, LM3886. This is in their Overture series amplifiers, and they come in a little package like this. And these amplifiers can deliver 50 to 60 watts typically, and they're very popular. And I have done some amplifier designs with this IC at least 25 years ago, and they're still a popular IC. This is a popular circuit board that's available on eBay, Amazon, and I recently purchased this amplifier, and I purchased this on eBay. It was $70, and with $30 shipping. The ad looks like this, and this is a pretty clever looking amplifier in that it has a built-in linear power supply. So we're going to take a look at it. About 10 years ago, I did an amplifier with the LM3886, and it's this beast right here. And it's kind of ugly, but there's a reason for that. At the time, I was working for a manufacturer that had products that had used these big heat sinks, these power supplies. This is a power supply made by XP Power. It's 36 volts and 300 watts. And you can see that I've got one on each side. And I made a couple of these, and we called them the trash amp, in that this company I worked for, when they had products that failed, and there were visual blemishes on the heat sinks, or problems with the power supplies, they basically threw them away. So these heat sinks, the power supplies, this metal are all components that I fished out of the garbage can or the dumpster, and so we call this the company trash amp. So this is probably 10 years old, and I'll show kind of the insides of this. And the little circuit boards right here, this is a stereo design. These are circuit boards that I made probably 20, it might be 25 years ago. So like I said earlier, I just ordered this, just received it a few days ago, and for $70 and $30 shipping, so 100 bucks. It's quite heavy. The construction seems nice. It's pretty thick aluminum. Volume control knob feels really nice. It's got some cute little banana plugs on it. Pretty basic. I haven't turned it on yet. I'm going to look at the inside first before I power this up. 3 pounds, 14 ounces. There we have it. We're in. And it's a nice looking design. Cute little toroid transformer in here. 40 volt, 4700 microfarad caps, so roughly 10,000 microfarads on the positive and negative rails. There's a full wave bridge down here, so we've got a circuit board for the AC to DC. Shielded wires coming from the audio jack up to the front, shielded going back to the board, and A little bit of a cause of concern for me in that it does not look like the AC input is fused going up to the transformer. So before I turn this on and plug it in, I'm going to add a inline AC mains fuse. This is a standard schematic for the LM3886. As we can see, it's a pretty simple design to work with. There's just a few external parts required for basic operation. We have the feedback resistor and the input resistor. These will set the gain, and we show that they show that this is capacitively coupled to block low frequencies from being amplified. And they also show that you should have these bulk decoupling caps placed near the amplifier. And I have, in my experiments, seen that these capacitors are very critical. And then we have this input. This is our volume control. So what's interesting is that there are some other components that should be added to keep the amplifier stable, and they show these on their single supply operation but not on their dual supply operation, which is a little odd. Primarily, there's a couple of things that we probably should add. Now, I didn't add these to my 25-year-old design, but probably should have. We have this network right here, and we have this network here. And what these do is increase the stability of the amplifier when it's driving highly capacitive or inductive loads. So these would be recommended to have. Some people will go, oh, I don't want to put a 10 ohm resistor in series with my speaker, but we have this inductor that's in parallel, and at low frequencies, basically this inductor is shorting out this resistor. So this resistor does not come into play until we get into higher frequencies. We're going to look at this eBay amplifier. I have the cover off, and I have inserted a 5x20 millimeter fuse right here. That's just kind of one of my rules. AC powered devices should always have a fuse on the AC line. This is my load. These are, each resistor is 8 ohms. It's rated for 50 watts, and I've got it on this big massive heat sink. This is a load I made to test multi-zone amplifiers a while ago. Oh, you can also see here that this is the ambient temperature of my work area, 18 degrees C. Here's the amplifier, and you can see we've got the audio precision unit. I'm going to do my initial measurements at 1 watt of power. That is 2.8 volts RMS into the 8 ohm load. You won't be able to read it, but this is showing 2.8 volts, and I have a peak of about 4.1 volts right here. You can see here that our output voltage is 2.8 volts. You square that, and that gives you 8 divided by 8 ohms. That's 1 watt. And to get that 1 watt, we need to provide an input voltage of 135 millivolts. I currently have the volume control knob turned to maximum. So we can see what our gain is in dB. We're 26.3 dBs. We can look at our signal to noise ratio, approximately 76 dB. I like to typically make my measurements at 1 watt of power. We could make this number appear higher just by increasing our input voltage. Let's go to THD. That's 0.02%. That's a pretty good number. Let's look at our generator load, or our load to the input to the amplifier, and it's greater than 20 kilo ohms. There's my AC mains, approximately 120 volts. We're running at 3.3% distortion, and pretty much 60 hertz. So let's do a frequency response curve. I'll put this into dB reference. We'll zero the reference, and we can run a sweep. So one thing I've noticed with this amplifier is right now we're running 1 watt of power, and it is very hot. Okay, so we are getting a little bit of a roll off here. That's primarily going to be a function of the input impedance and the input capacitor. So our 6 dB down point is about 17 hertz, not an issue. And we're flat up to almost 20 kilohertz. 6 dB down point is roughly, I'd call it 23 kilohertz. Let's do a sweep of the THD and see if we see anything interesting. So that is a little interesting here. We have this little drop here in the THD. Interesting. Let's look at some thermals of this amplifier. Right now I'm pointed on the tab of the LM3886, and I'm measuring just shy of 60 degrees C. So this is quite hot, and we're just driving 1 watt. If we look at the toroid, let me see if I can get the focus there. 50C on the edge. This is the full wave bridge at 47C, and back to the LM3886. Let's look at the voltage on the main power rails. This is 1 watt with both channels driven, and we are plus and minus 34 volts. I'll remove the input voltage, so now we are basically 36 volts, and our filter capacitors are rated at 40 volts, so that's a little closer than I would like to see them. Let's just do a double check on the temperature of the LM3886 just to verify if our emissivity settings are wrong on the FLIR. So I'm going to poke my thermal probe down here on the top of the tab, about 63C, so 65C, so pretty close. Let's go over here on the side. Say it's uncomfortable to hold on to this chassis. 47C on the side, and let's look at the bottom, right where the tabs of the LM3886s are. Here is what our square wave response looks like into about 1 watt, and the square wave looks pretty clean. I'm going to put a 0.68 microfarad cap across the load and see if we have any stability issues. That's possible that if we added some of the additional circuitry around the LM3886, it might not have that issue. Let's pull it back off. We're going to drive this into clipping now and see how much power we can get and see what happens when we get to that clipping point. I'm going to increase my voltage. Right now I am 12 volts RMS. Right there we're starting to see some fuzz down here. This is both channels driven, so we are getting approximately 17 volts. Top of the waveform is starting to get a little fuzzy, and it's might not be able to read it, but we're 18 volts RMS. I think our voltage on our power supply is sagging, and so that's why we can't get any more voltage out of that. In this condition, I'm going to look at what our power supply is providing, and we are 26 volts. Wow, that's really sagged quite a bit. Okay, I just finished those clipping tests, and I can barely even touch the chassis right now for maybe just a second. It is smoking hot, so I don't know. I wouldn't want to keep this on much longer. This is the tab of the LM3886. So here you go. Here's the problem. Right now I am supplying 1 watt of power to each of these loads. So across each one of these loads is approximately 2.8 volts RMS. Each load is 8 ohms, so that's the 1 watt here and here. And I am pulling from the AC mains 29 watts. 2 of those watts are over here. 27 watts are going to be inside this chassis. We need a fair amount of heatsink for just 1 watt of power. Well, what can I say? It has a couple of flaws. First flaw is it does not have an AC fuse, which I think it should have. Since it has AC coming into the chassis, I believe this chassis should be earth grounded. It is not, because it only has line and neutral. And in my opinion, it's going to get way too hot. As we saw with 1 watt of power into both channels, this device needs to dissipate 27 to 28 watts, and it's just going to get way too hot. You know, if you were using much lower levels, it probably would be okay, but if you start driving a few watts, I think it's going to get just way too hot. Other than those flaws, it's a nice sturdy chassis. Volume pot works well. It's acceptable audio characteristics. It sounds like an LM3886. Yeah, that's about it. Yeah, for that $70, it might be worth it if you want to do some modifications. So a modification that you might try is you could put this front panel, you could undo the 4 screws, rotate that 180 degrees, flip this upside down, take these stick on, these feet, put them on the back side, and it probably would do better at dissipating some heat. And better yet, you could take a couple of heat sinks and put some heatsink compound on that, screw those into the chassis. You could attach them with some thermal epoxy, maybe even some thermal tape, and a couple of heat sinks. If you had a heat sink that was like this and maybe a little longer, I think you would be fine for its rated power. Well, there you have it. I am going to do another video with some other LM3886 projects I've got, and we'll see if we can see any differences and make some improvements. Thank you.